Hi, everybody. This is Lecture 13 of Privacy in Machine Learning and Statistics, where we're going to start kind of a unit of the course where we're going to focus a lot on the linear query release problem. And we're going to start this lecture by kind of recapping linear query release and giving kind of a different perspective on the problem that will be really useful. And then we're going to get into seeing some of our sort of our first kind of general non-trivial method for query release. So far we've talked about the Laplace and Gaussian mechanisms for query release, and this one kind of special example of the binary tree mechanism. And what we're going to do today is we're going to introduce kind of a more sophisticated framework for linear query release that captures the binary tree mechanism and lots of other interesting things you can do, and forms sort of the basis for the algorithms in use by the US Census Bureau for the 2020 decennial census, which of course are somewhat more involved than the basic mechanism we're going to cover, but we're going to be able to talk about a lot of the ideas that go into it in this and the next lecture. So to start, let's recap linear query release, which we've done a couple times in the course, but let's make sure that it's right at hand. So I'm going to start by just reviewing the problem, and then I'm going to kind of do it all again in a different notation. And I think you'll see why by the end of the lecture that we're going to do this. So remember, linear query release is a problem that captures statistics of the form how many people in the data set satisfy some property. So how many people in the data set are African Americans living in Maryland who are over the age of 36, that kind of question. And each one of them on its own is a fairly simple statistic. There's not a lot to say about it, but when you put together large tables of these things, you get really rich demographic information. So let's recap the problem, and I'm going to make just a few little changes from the way we've studied it before that are going to be useful, and I'll talk about what they are. So if you remember, we have our data set X, which is x1, xn, and each element of the data set comes from some universe U. All right, this is all the possible elements that the data set can contain. And we're given statistics f1 through fk, and each fi is defined as 1 over n times the sum over all of the records in the data set of some function that maps each possible record to a real number. So I've made two little changes here to be aware of. So first of all is I'm going to normalize by the size of the data set. And this is really just notation, because the way we've modeled differential privacy, we assume that data sets all have size n, and so we can freely divide by n and multiply by n. It's just useful to do this because, well, we'll see in later lectures exactly why it's useful to do this, but all that's important to remember is that now we're not going to compute the sum of the function over the records of the data set. We're going to compute the average. So instead of asking how many people are left-handed residents of Massachusetts, we're going to ask what fraction of all the people in the data set are left-handed residents of Massachusetts, but I can go between the two. Okay, so it'll hopefully be clear why we want to do this. And the second change is that I'm not actually requiring that the query is a count. So I'm actually going to let the query take the average of some function that maps users to arbitrary real numbers. So I'm going to allow that, I assign, let's say, like I can look at something like the average height of people in the data set, where phi maps your record to the height, which might be a number between 0 and 300 centimeters or something like that, depending on how you scale it. Okay, but I will still refer to counts. When I say counts, I'm still referring to things that output 0 and 1, which is useful because it gives us some easy bound on the sensitivity. All right, so that's my second change. Like, I'll allow things to be arbitrary real numbers, and again, there's a reason why I'm going to do this. And lastly, I'm going to change the goal just a little bit. So we want to find a vector of answers to all the queries. And before I said that the answers should be close in the sense that for every query, AI should be close to fi of x. I'm going to change the game just a little bit, and I'm going to ask for these vectors to be close as in L2. So what I mean by that is I now want that the sum over all the queries I of fi minus, fi x minus ai squared to be less than alpha. So this is the L2 norm of these like vectors. And I'm also going to take the average over all the queries, because that way, if I have error alpha on every query, this overall L2 norm will be at most alpha. So it kind of puts the L2 norm and the maximum error on the same scale. So this is our second change. We want L2 error. Okay, so we look at the answers that we get, and we write them as a vector, and we look at the true answers to all the queries, and we write that as a vector. And we want that the L2 norm of that vector, suitably kind of rescaled by the number of queries, is at most alpha. So this is kind of like saying that on average, the error per query is about alpha, instead of requiring that every query is at most alpha. All right, and this change is like not going to be like exactly inherent. It's just going to make some of the math a little easier to work with, in my opinion. It's a little more natural for what we do. And lastly, just to be concrete about this, let's define like the sort of vector of queries. And the thing we want is that if I take this vector minus a in L2 norm divided by square root of k, I want this to be at most 1/2. So that's why I'm calling this L2 error, and why I'm saying that we're kind of suitably scaling it. Okay, that's the linear query release problem that we've introduced with a few of these little tweaks that I highlighted in red. Okay, but some of them are not like particularly fundamental. They just make the math a little more natural, in my opinion, for what we're going to talk about in the next several lectures. Okay, so this is like 99% recap, 1% little notational tweaks. Don't worry, we're going to do a lot more notational tweaks. This lecture is all about notational tweaks. So let's recall how we solve this using the Gaussian mechanism. So I'm going to focus on epsilon delta privacy for this lecture and the Gaussian mechanism, because I like working with Gaussians. But everything I'm going to say, if you have suitably changed the parameters, we could do this with the Laplace mechanism. I'm just doing the Gaussian mechanism because I just think it works nicely and is a little easier to analyze, and it gives us better bounds in most cases when we're answering a lot of queries. But nothing I'm saying is really intrinsic to Gaussian. So I'm going to recap the Gaussian mechanism. Okay, so if remember, the Gaussian mechanism is mx outputs the vector of answers plus some noise z, where z is some normal that has z adds noise that is Gaussian with variance sigma squared to every coordinate. And the way we set sigma squared is that it's going to be equal to the L2 sensitivity squared times some constant that depends only on epsilon and delta. Okay, so I want to roll this into a constant just because otherwise it gets really irritating to write that the variance is the L2 sensitivity divided by epsilon squared times log 1 over delta or 2 over delta or something like that. It's just a pain in the butt, so I'm just going to write this constant c that depends on epsilon and delta, and it's going to sort of capture the epsilon and delta. So what that should kind of suggest to you already is that nothing we're going to talk about is really going to have any effect on epsilon and delta. The dependence on those parameters is always going to be the same. What we're really interested in is how we can get better error bounds for queries with nice structure. We're always going to sort of get the error to scale with this constant depending on epsilon and delta. It's just not going to be the interesting part. Okay, so I just want to suppress it. All right, so this is the mechanism. Remember, I'm adding noise with magnitude sigma squared, variance sigma squared to every coordinate independently from a Gaussian. And the way I calculate the L2 sensitivity is I'm looking at the maximum over all neighboring data sets of f of x minus f of x prime in the L2 norm. Because I'm working with Gaussians, I want L2 sensitivity. And because my statistics are linear, this is just equal to the maximum over u and u prime in the domain of of 1 over n times f of u minus f of u prime. Okay, so why is this? Well, imagine that u is the thing that I delete from x, and u prime is the thing that I add to x prime. And because these statistics are linear, what I'm doing is so it should be backwards, but it doesn't matter because it's absolute value. I'm just subtracting off an f of u prime, and I'm adding an f of u. That's the difference between f of x and f of u prime. And by the triangle inequality, this thing is at most the max over everything in the data set, everything in the universe, of what happens when I apply the queries to just this data set of size 1, consisting only of the element u. All right, and since f is just a vector of a bunch of queries, if these are counts, we can say that this is at most 2 square root of k over n. Okay, so we can write this as 2 root k over n if we know that the queries are outputting values in 0 and 1. But it might be smaller, it might be bigger. I just want to give you some sense of the scale of what the sensitivity is. Right? And I want to make myself a little more space. And the error of this mechanism is just the expected L2 norm of this vector z divided by k to the 1/2. Because remember, I normalized the error by k to the 1/2. And that thing is equal to, or is at most, c times epsilon delta times sigma, where the 2 norm depends on k over 1/2, but the dividing by k to the 1/2 gets rid of it. So basically this says that for every coordinate, the noise is about c of epsilon delta times sigma. All right, and so again, if these are counting queries, this is c of epsilon delta times k to the 1/2 over n, 2 times that. Okay, so again, for counting queries, we already knew that we could add noise about square root of k over n. times some constants depending on the privacy parameters. Okay, so I just want to refresh, sort of map this back to things we understand so that we don't get confused. But the important thing is that the sensitivity is, or sorry, the L2 error, as I've defined it, is at most this constant depending on epsilon and delta times the L2 sensitivity of the function. Okay, that's just what we've said about the Gaussian mechanism. So I'll just recap at this point. So good. So far we've just done recap, maybe with a few little tweaks. So let's do it again in a different notation, which is going to be really helpful for understanding the structure of the queries. And it is also finally going to explain why these are called linear queries. When I learned about this, I hated this term because they're not linear. The query seems like it should have something to do with phi, and like phi is not a linear function. But we're going to see like in what sense the queries are linear. And hopefully that will like demystify something a little bit. So let's, recap. So we have a data set, and it's xn in U, and the domain is, I'm going to just say sort of without loss of generality, it's like numbers between 1 and m. Okay, so the important thing is just that m is some set of size, or U is some set of size m. Okay, and I'll think of it as finite. I don't want to think of it as infinite. All right, so now I'm going to replace this data set and domain with what's called the histogram of the data set. So the histogram is going to be some h sub x, and it's going to be an element of r to the m. Okay, so it's a vector of length m, where m is the number of possible domain items. And it's defined as hx of u is equal to the number of j such that xj equals u. Okay, so if you think of this data set, let's say the universe is 6 possible things. So everyone's data is a number between 1 and 6. This histogram is a 6-dimensional vector that says, I should say what fraction of people in the data set are of each type. So what fraction are 1s, what fractions are 2s, what fractions are 3s, what fractions are 4s. So for example, if the universe is 1, 2, 3, and x is 1, 2, 3, 3, 1, then the histogram is 2 over 5, 1 over 5, 2 over 5. Okay, because out of these 5 records, 2/5 of them are 1s, 1/5 of them are 2s, and 2/5 of them are 3s. All right, and of course, if I have the data set, I can always write the histogram. If I have the histogram and I know n, I can always write the data set up to the order. Okay, so if I see a histogram, I know how many 1s, 2s, and 3s are in the data set. I don't know what order they should be in. But the queries we're interested in for today don't care what the order of the data set is. They're symmetric with respect to the order of the data set. So for today, it's worth just thinking of the histogram and the data set as being in one-to-one correspondence. There's no, the only way that a histogram is unclear about what the original data set was is we don't know the order of the records in the data set, but we also don't care. It's enough information to answer the queries. Okay, so 2 important facts about histograms are that for every data set, the histogram is a vector whose L1 norm is 1. Okay, so in particular, every entry is positive, so the L1 norm is just the sum of the entries. And because I've normalized by n, the sum of the entries is 1. Okay, so just keep that in the back of your mind. It's a vector whose entries sum to 1. Okay, and second, if x and x prime that are neighbors are neighbors, then when I change like one record of the histogram, or sorry, one record of the data set, then, well, I'm gonna, in this case, subtract 1 over n from the 1's column, and then I'm gonna add 1 over n to the 3's column. So if I look at the difference between these two vectors, there's one entry where I subtracted 1 over n, and another entry where I added 1 over n. So that means that the difference between the two histograms in the L1 norm is at most 2 over n. All right, so when we talk about neighboring data sets, we talk about swapping one row of the data set. In kind of histogram land, what that corresponds to is changing the histogram by some small perturbation whose L1 norm is about 2 over n. All right, so that's sort of the key notion in which changing the data set by one record changes the histogram. So it's worth keeping in mind that kind of neighboring data sets correspond to like neighboring histograms, where neighboring histograms kind of means that we change the histogram by about 2 over n in the L1 norm. All right, so lastly, we can talk about like queries in this language. So given queries, f1 through fk, and which are like defined by these phi1 through phi k, we can write a matrix. So we can write f of x as a matrix vector product, f times the histogram of x, where f is defined as follows. Whoops. So f is a matrix, and the way I define it is that each row corresponds to one query. And what I do is I put like the universe item, I put like the evaluation of the query on all the universe items. Okay, and second row is the second query. And then finally, the kth row is the kth query. All right, so a good exercise is to check for yourself that these two things are equal. So, so first of all, that's right. So F is a matrix in R k times m. So just keep that in mind. And an exercise is check that f times hx is like the queries evaluated on the data set. All right, I'm going to go on, but you can check that for yourself. I want to make one comment about the histogram representation, which is that it's really not a good way to represent a data set if you care about actually implementing the mechanism. And the reason is that the number of universe items can be extremely large. So if you imagine we have a data set that has, say, n equals 100, and let's say that each person's data is 30 yes or no questions. So each person's data is a string of length 30 of zeros and ones. So to represent that data set, I have, 100 people times 30 bits. So that's 3,000 bits to represent the data set. So like a very small data set. But if I write it as a histogram, my histogram has 2 to the 30 buckets because there's 2 to the 30 different ways that a person could answer all 30 questions. And 2 to the 30 is over a billion. So my histogram has a billion buckets. And if I went up to 40 bits per user, then my histogram would have a trillion buckets. So the histogram itself is a huge and like sort of unwieldy object. And so we don't really want to like design mechanisms where we have to write down the histogram explicitly, but it's a useful way of thinking about the data if we want to analyze the best error versus privacy trade-offs we can get. Okay, so in general, we don't really want to actually like write the mechanism in this sort of notation, but it's a useful notation for understanding what we can do with differential privacy, and also for just thinking about how what a good mechanism might do. So that's the histogram representation. And lastly, let's do the Gaussian mechanism in this notation. Okay, so first of all, the Gaussian mechanism in this notation doesn't change, right? We still have that m of x is now this matrix vector product plus z, where z is chosen from the following Gaussian distribution, where I output noise on every query with variance sigma squared. So, I'm not changing the mechanism because I'm not actually changing how I compute the queries. The answer to the queries is the exact same thing, whether I treat it as a matrix vector product or just the answers to the queries. Okay, so the mechanism doesn't actually change. However, let's suppose we had never thought about the let's suppose we'd like never thought about the Gaussian mechanism and linear queries before. We had just defined the queries this way. Okay, so we want to know how much noise we have to add, and the amount of noise we have to add is, again, sigma squared, which is this like thing that depends on the privacy parameters, times the L2 sensitivity. And like, what is the L2 sensitivity? So the L2 sensitivity is max over neighboring data sets of f times the histogram on one data set minus the histogram on the other data set. All right, and as we said, these are two histograms that are like 2 over n apart, like in the L1 norm. So this is just the product of a matrix and a vector whose L1 norm is bounded. So this is like the max over v in r to the m, such that the L1 norm of v is at most 2 to the n of f dot v. And this is, by renormalization, 2 over n times the max of v in Rm, such that the L norm, the L1 norm is at most 1. In fact, I can even make it equal to 1. It doesn't really matter. So, again, sorry, of f dot v. Okay, so I just renormalized. I made v bigger and I divided by 2 over n. So, good. Now, this doesn't seem particularly helpful. However, this thing is equal to 2 over n times largest L2 norm of a column of f. And it has a name, but I don't want you to get overly hung up on what this thing is, but this is sometimes called the 1 to 2 norm of f. So it's just a special, like there's just a notation, there's a norm called the 1 to 2 norm, and it happens to be equal to the largest L2 norm of any column of the matrix. And why that's called that is something you can ask me about offline. It's not really that important, but I want you to just like remember this notation. And the reason I want you to remember this notation is because if I give you a bunch of linear queries defined by the matrix F, the L2 sensitivity is proportional to that thing. Okay, so you can just think of this as notation for the L2 sensitivity of the queries defined by F. There's a reason why this norm has this name and why it's like a nice thing that comes up, but for now, you can just treat it as special notation for the L2 sensitivity of the queries defined by the matrix F. All right, so yeah, just deal with that. And one thing you can do is you can check that this is exactly the same as the quantity that I called the L2 sensitivity before. There goes a cat. So this is the L2 sensitivity. And now, like in this notation, we can also say that the error of the Gaussian mechanism is like the expected value of m of x minus f h of x divided by k to the 1/2. And that is at most sigma, that is at most sigma, which is at most c epsilon, or equal to c epsilon times delta 2, which is equal to 2 times c epsilon delta times this like 1 to 2 norm over n. Okay, so again, this is just like exactly the thing we said before, except in this matrix notation. So, good. Take some time to digest this histogram notation. So far, it's literally just notation. Okay, so like just to appreciate what we've done for the last half hour, I've recapped query release and the Gaussian mechanism, and then I've done it again in a different notation. All right, so in the next lecture, we'll see how thinking of M as this, or thinking of the queries as this matrix F is going to let us do certain transformations on the queries that's going to be really useful for improving the error for query release. And it's going to capture things we've like already seen. So